In previous videos, we've looked at using the constant acceleration equations to solve problems in one dimension. We're now going to move our work on and look at solving problems in two dimension using vectors. Let's start off with a brief recap of what we call the constant acceleration equations, or SUVAT equations. One of them is v is equal to u plus at. V is the final velocity, u is the initial velocity, a is acceleration, and t is the time. So we can say v is equal to u plus at. We also saw that s, the displacement, was equal to ut plus 1/2 at squared. S is the displacement, u is the initial velocity, t is the time, and a is the acceleration. We also saw that s could be written as u plus v divided by 2 multiplied by t. These are the three main equations we're going to use when we're working in two dimension with vectors. I'm going to put this one as number 1 and this one as number 2. The third one we might choose, but certainly we're going to use these two. This one, when we're working in two dimension, remains the same. V is equal to u plus at. The final velocity is equal to the initial velocity plus acceleration multiplied by time, where the acceleration is constant. What I'm going to do is rewrite equation 2, and I'm going to say that r, which is the position vector, is equal to r0. r0 is where it starts, plus the ut plus 1/2 at squared. So all I've done is swap the displacement for this value here, which is going to be our position vector. Sometimes you see in books r0 put at the end. That's perfectly fine. I put it at the beginning just in case I forget to add it on. So if you only remember two equations now for this particular unit, remember these two. We can of course change this one. R, where it ends up, so this is the position vector of where it ends, is equal to r0, this is where it starts, and then we're going to have plus u, the initial velocity, plus v, which is the final velocity, and that's going to be divided by 2 multiplied by t. So if you want to, you can put that one down, but it's these two that we really need to be able to apply and, well, remember them. I'm going to apologise now that my R's look a bit like the V's, but hopefully that should make sense for you. Okay, let's also look at some basics. When we're talking about the vectors I and j, the vector I is going to be in the x direction, or, if we like, due east. This is a unit vector, which means it has a magnitude or size of 1. J is going to be in the y direction, or we can say due north. So if I just change that over, let's change that to a vertical and we'll make that go upwards. So that's what we've got. So I and j notation, which we looked at in the last video. We can also say the vector AB is going to be equal to B minus A. So for example, if I wanted, now I had some point A, and A was in column form, let's say 1, 3, and B was going to be 7, 2, we could say now for the vector AB is going to be now 7 minus 1, which is going to give us 6, and then we're going to have 2 minus 3, which is negative 1. So this is another thing. We can employ this if we need to. So let's go ahead and look at some questions involving these. Each time we do them, I strongly suggest you just write the information, capturing it with SUVAT, and then use one of these two equations to solve. So the first question, we're told that points A and B have position vectors 3i plus 2j meters and 6i minus 4j meters respectively. The vectors I and j are in a horizontal plane. In part A for 3 marks, it says a particle moves from A to B with constant velocity I minus 2j meters per second. We're asked to calculate the time that the particle takes to move from A to B. Let's just look at this I and j notation. I prefer to write these as column vectors. So we have 3, 2, and we have 6, negative 4. If I wanted to look at this as a velocity vector, remember these are given as position vectors. So if we wanted to draw these up, let's just go ahead and quickly sketch these. 3, 2, we go across 3 and up 2. 6, negative 4, we go across 6 and down 4. So we could put these on in either form. This here is a velocity vector, and we could write this as 1, negative 2, and that's going to be meters per second. Lots of the work we're going to do in this video, I'm going to use the column vectors, but do be able to work between the two. I appreciate some exam boards prefer this approach, some will allow you to use the column notation. So let's look at this one right here. So what we want to do is find the time. So all I'm going to do is use SUVAT. So S, U, V, A and T. You certainly don't need to do this, but it might help. If we look, we've got a constant velocity. Constant velocity is going to give me an acceleration of 0. We've got an initial velocity of 1, negative 2, and we're trying to solve for t. In terms of this particular question, this differs slightly. What we could use is r is equal to r0 plus ut plus 1/2 at squared. This is one approach. I'm going to do it a slightly quicker way shortly, but if we wanted, we could simply do this. So if we look at this now, we're going to end up at the point 6, negative 4. We're going to start at the point 3, 2. Then I've got ut. Well, we know that u is 1, negative 2, and we're going to multiply that by an unknown t. If we consider at this stage now, a is 0, so this part of the equation is not applicable. We're going to have now an equation for the I component and also for the j component. These should be consistent. So if we solve for the I component, we can see that 6 is equal to 3 plus t, so we can say from that t is equal to 3. I could have gone ahead and solved for the other one. So the j component, we equate those and we say that negative 4 is equal to 2 minus 2t. Subtracting 2 and dividing by negative 2, t will of course be 3 as they're consistent. Another approach for that one is to find the vector AB. So if we have the vector AB is b minus a. So if we think about this now, b is 6 minus 3, that's going to give us 3. And then we're going to have on here, we've got negative 4, and then we're going to subtract 2, that's negative 6. So with this one, we could have just said that r now is going to be equal to u multiplied by t, with this being r. So if I do that, I can simply sub this in, and we can see that we're going to get now 6, negative 3, as we've got a constant velocity. So this is simply going to be now 1, then we can have the negative 2 multiplied by t. And we can see it holds nonetheless. So for that particular question, I think it's easier just to find the vector AB and see that it doesn't have any acceleration and do this approach. But if you're not confident, just substitute it in here and you can solve. This will always work in terms of constant acceleration in 2 dimensions. Okay, so that bit's done. We've done that. And on here, so we found the time, so that's going to be t is equal to 3, and we just conclude by saying 3 seconds. Remember, we're dealing here with seconds, so t is going to be 3 seconds. So just jotting this down, 3 seconds. So that now will be the first part done for 3 marks. In part B, it says the particle then moves from B to a point C with constant acceleration of 2j meters per second squared. It takes 4 seconds to move from B to C. In the first part for 4 marks, we need to find the position vector of C, and in the second part, we need to find the distance AC. So if we collect this up using SUVAT, so again, you don't have to do this, but it might help. So what we're going to have is the following. We've got a time, that's 4. We've got an acceleration. This is 2j. In column form, that's 0, 2. We have now an initial velocity. So the initial velocity is going to be this one right here, because it was constant from A to B. So that will have remained to be 1, negative 2. What we're going to do is find the position vector of C. So all I'm going to do is go back now to this one right here, and we're going to say that C, and I'm going to put this now, C is going to be PQ. You certainly don't have to do that, but hopefully you'll see what I'm going to do. So where did we start? Well, we started at B. That's R0. Where we ended up are P and Q. P is the I coordinate or I component, J is Q is a J component. So we started at 6, negative 4. We're going to add to this now ut, which is 1 minus 2, multiplied by 4, plus 1/2 at squared. And I'm just going to squeeze this in as I'm running out of a bit of space. So this is this part right here. 1/2 of acceleration will give me 0, 1. And then we're going to have t squared, which is going to be 16. So if I just bracket this off, hopefully that makes sense. All I've done is taken this equation right here and substituted in the values. Where we end up is where we start plus the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by the time squared. So from this we can equate I components. So when I equate I components, P will be equal to 6 plus 4 plus now the 0. So all I've done is said P is 6 plus 4 times by 1 plus 16 times by 0. Again, if you're working with I and J notation, you might do this a slightly different way. So what we can say is P is equal to 10. If we equate the J components, we can say that Q is going to be equal to negative 4. Then we're going to have now minus another 8 plus 16 times by 1, which is going to give me that Q is going to be equal to 4. So we can write that just here, and I'm going to say now that C will have the point, and we can write this on here as C will be 10I plus 4J meters. So that gives me my position vector relative to a fixed origin. So in this particular case now, if we were at the origin, the original R0 would be equal to 0, 0. So that's what we've done. Okay, we now need to find the distance AC. So if we think about the vector AC, AC is going to be equal to C minus A. So we've got C in column form as 10, then we're going to have 4. We're going to subtract from that A. We've got A, which is going to be 3, 2. So that gives me now that we have the following. So we can say that the vector AC is going to be now 7, 2. And all we need to do is say that AC, and we'll put it now as the modulus of AC, is going to be 7 squared plus 2 squared. This is simple Pythagoras, as we've seen time and time again. So that's 49 plus the 4, which is root 53, which should give me about 7.3, I guess. So let's have a look at that. So on the calculator, the square root of 53, what have we got? 7.28. So this is going to be 7.28 meters. All we've done essentially here is looked at a point and used a right angle triangle. So if I just pick that up, what we've got then is the following. We've got this point here, 10, so C is going to be 10, 4, which we'll put just there, and then we've got 3, 2, which we'll put just here. So all I've done is looked now at the distance between the two using a right angle triangle. This length here is 7, this length right here is going to be 2, so the hypotenuse of that, using the distance formula, is going to be the square root of those 2 squared. So quite a nice question there, and in total 9 marks. As you can see, I'm using these column vectors. Feel free to use I and J notation. Okay, in the next one, we're told a particle is initially at the origin where it has velocity 5I minus 2J meters per second. It moves with a constant acceleration A meters per second squared for 10 seconds to the point with position vector 75I meters. In part A for 3 marks, we need to show that A is 0.5I plus 0.4J. Let's just collect the information using SUVAT. So if we have SUVAT, we can say now the following. So we've got the initial velocity, so we've got the initial velocity of 5, negative 2. We've got some acceleration, and I'm just going to use PQ, and we've got some time, which is going to be 10. So I've got this position vector, so using now R is equal to R0. Where we end up is where we start, plus UT, plus 1/2 AT squared. So where did we end up? Well, we ended up now at 75I. So 75I is 75, Where did we start? Well, we started at the origin, which you can omit. I'm just going to put it in. The only reason I'm putting it in is so I don't forget it in later questions. to do that. Often students forget to put it in, as it's not in S is equal to ut plus 1/2 at squared. So now what we're going to do is look at ut. So that's going to be 5 negative 2 multiplied by t, which is 10. Then we're going to have plus 1/2, and I'm going to use p and q. P is going to be the I component of acceleration, q is going to be the j component, and that's going to be now 10 squared. So this is just t squared, so that's 100. So if we look now at the I components, 75 must be equal to 0, plus 50 plus 50p. So subtracting now the 50, we can see that 25 over 50 will be equal to p, and we can say from here that p is going to be equal to 0.5. So p is equal to 0.5. If we now consider the j components, we've got the following, so let's write this on. J components, 0 is going to be equal to 0 minus 20, and then we're going to have plus 50q. So from here now we can see if I just add the 20 to both sides, 20 divided by 50 is going to be equal to q. So we can see from here that q will be 2/5 or 0.4. Therefore we can say now that A is going to be equal to 0.5 I plus 0.4 j meters per second squared. So any way you want to answer that question is perfectly fine. I like to do it like this, but there are of course alternatives. In part B for 3 marks, we need to find the position vector of the particle 8 seconds after it's left the origin. So let's just collect the information, so that. So we've got a time of 8 seconds. We've now got the acceleration, and in column form this is going to be, and we could write it as 1/2 and 2/5, or in decimal form if you like. We've got the initial velocity, which is 5 negative 2, and we want to find now the position. So all we're going to do is use this one again. So I'm going to have where it ends up, r, is where it started. Adding this in, 0, 0, plus u, which is 5 negative 2 multiplied by the 8, plus 1/2 of a, which is going to be 1/4, and I'm going to write this in 1/4, and then we're going to have now 1/5 multiplied by t squared, which is going to give me now on here 64. Just be a little careful, I'm doing this as I go because I'm running out of space, but essentially that's what we would have. So again, if you wanted to now look at this as r, so you could write now pq here, pq, that will give us the position. So if we equate I components, p is going to be equal to 0, plus now the 40, and then we're going to have now on here 64 over 4, which is going to give me 16. So this is going to be equal to 56, and we can put I. That is now giving me the I component. The j component, q is going to be equal to 0. We've got now negative 16, and then we're going to have plus 64 divided by 5. What's 64 divided by 5? 12.8. Let's just check that. 64 divided by 5, and that's going to give me on there 12.8. And then of course all we need to do is from that, so 16 minus the 12.8, and then we will get our value. So negative 3.2, and that's going to be, so what do we want? Let's see the other way around. Negative 3.2, so negative 3.2 j. So if we wanted to write this down, we can say now the position is 56i minus 3.2 j, and that's going to be meters. I always like to conclude in this form. I think it looks nice, and I've given the correct units. In the next part, for 6 marks, we need to find the position vector of the particle when it's travelling parallel to the unit vector I. Let's just think about this. We can clearly see there's a lot of work involved for 6 marks. If we think about this reasonably, if something is travelling parallel to the unit vector I, it's travelling now parallel to the x-axis. So we can see from here that any of these, and I'll call them, let's just put them on, let's say this is going to be V1, we'll say this is V1, this is V2, this is V3. The thing that's consistent about these now is that the j component will be equal to 0 in the velocity. We're gaining no vertical or anything in the y direction. So if we're travelling parallel to this, we can say that the j component will be equal to 0. So we need to find the position vector. So what I need is a double application. So I'm going to use now SUVAT. So taking the information again, we've got the following. So we know our acceleration is given to be 1/2 and 2/5. We've got now the initial velocity. The initial velocity is going to be equal to 5 negative 2. So let's go ahead and do that. So 5, and then we're going to have negative 2. And what we're looking to do here is now set the j component of the final velocity equal to 0. So I could just define the I1 to be p and that one to be equal to 0, and we can find t. Once I've solved for t using v is equal to u plus at, I'm going to substitute that back into here to find now the position. So let's go ahead and use this to find t. So what we can say then is p0. This is the velocity vector. Remember, there is 0 in the j direction. We got 5 negative 2, and then we're going to add to that 1/2. And again, you might be working in decimals here. So here, I'm not interested in this type of equation. I can't solve that because I've got two unknowns. All I want is the following. So what I can say, equating now the I components, we set those, the j components, we set those equal. That's negative 2 plus 2/5 t. So solving this equation from here, we can see that t is going to be 5 seconds. So a nice little linear equation solved. Now what I'm going to do is substitute this back into r, the position is equal to where we started, plus ut plus 1/2 at squared. So where we end up is where we started, and we've started at the origin, as we're told here. So started at the origin. Then I've got my value for t, so we're going to have plus u, which is going to be 5 negative 2 multiplied by the 5, plus 1/2 of the acceleration. Again, I can see that that would be 1/4, and then we would have now 1/5 multiplied by the time squared, which is 25. T is 5, t squared is 25. So again, we could put that r is just given as pq. You might want to do something else if you've used p before. I'm just going to put it here. We can now look at the I components. P will be equal to 0 plus 5 times by 5, which is 25, plus 25 over 4. So what's that going to give me? That's going to give me 125 over 4, or what's that, 32.125. Let's just try and do that. 125 divided by 4, and what do we get? 31.25. So we can say 31.25 I. If we now look at the j components, we can say that q is going to be equal to 0. Then we've got negative 10 plus 1/5 of 25, which is 5. So we can say that that is going to be now minus or negative 5j. So we can say that this is 31.25 I minus 5j meters. So a double application of the constant acceleration equations, but all I'm doing is collecting the information and substituting it back in. So nice little question. On that one, it's worth 12 marks. Okay, let's look at another one. A jet ski is at the origin, so that's good, we're at the origin, and is travelling due north at 5 meters per second when it begins to accelerate uniformly. So this is constant acceleration, that accelerates uniformly. After accelerating for 40 seconds, it is travelling due east at 4 meters per second. The unit vectors I and j are directed east and north respectively. In part A, we need to show that the acceleration of a jet ski is 0.1 I minus 0.125 j meters per second squared. Right, let's think about this reasonably. We can rewrite these. So initially, and I'll put this in, let's put this in, so that what we've got is the following. So it's travelling due north at 5 meters per second. So the initial velocity is 0.5. Just think about this reasonably. If we're travelling now due north from any point, then we're going to have 0.5. We could write this like so. If it's travelling due east, we're going in this direction, so this now would be 4.0. So we could put that on, and that would be 4.0. We want the acceleration, which we could call PQ, and we're given now a time of 40. So all I'm going to do at this stage is use v is equal to u plus at. So subbing this in, what we can say now in column form, 4 naught is equal to 0.5 plus the acceleration, and I'm just going to call this p and q. So p now is the horizontal acceleration, q is the vertical acceleration, if you like, or in the x and y direction, and then we're going to have multiplied by 40. So if we equate the i's, we can say that 40 is equal to, 4 is equal to 40p. Let's just change that. 4 is equal to 40p, and that's going to work out quite nicely for us. Let's not do that, that's a bit drastic. Let's grab that one, there we go. So 4 is equal to 40p, so we can simply divide both sides by 40, and we can say now that 4 over 40 is equal to p, and that gives us now that 0.1 is equal to p. So we show that one, that's fine. If we now consider the j components, so we're looking now at the j component of acceleration, 0 is going to be equal to 5 plus 40q, so q is going to be equal to negative 5 over 40, which is going to give us that value of negative 0.125. So that can be written like so. So negative 0.125, and that gives us q. So that's now our acceleration, and we've shown that simply by using v is equal to u plus at and subbing them in. In part B, we need to find the position vector of the jet ski at the end of the 40-second period. So 3 marks on this one. So position is where we start plus ut plus 1/2 at squared. So we've got the information here, and again we could call this C and D if we liked to say where we're going to end up. We started at the origin 0, 0 plus u, well u was given to be on here 0.5 as we were travelling due north, so due north, and then we're going to have now plus, multiplied by t, which is going to be the 40, plus 1/2 at squared. So if we want to write this, I can write this now as 1/2, and then we can have the acceleration 0.1 and negative 0.125, and then we're going to have t squared. Well, 40 squared is going to give me 1600. So what we can do is equate the I components. So C will be equal to 0, 0, and then we're going to have now 800 multiplied by 0.1, which is going to give me 80. You might want to show a little more work in the mat. All I've done is equated these 0, 0, and half of 1600 to 800. 800 times by 0.1 is going to give us 80. So J components, we can say that D is going to be equal to 200. So 200, and then we're going to have plus half. So what's that going to give me? That's going to give me 800 multiplied by negative 0.125. So let's go, what's that going to give me? 100. Let's just check that. I think that will give 100. Let's just put it in the calculator. Just to make sure, so 800 times by 0.125. So this is one way that you can do this question. Yeah, that'll give me 100. So D is going to be equal to 100J. So we can say now the position of this is going to be 80I, and then we're going to have plus 100J, and that's going to be meters. So another 3 marks on that part. In part C, it says the jet ski is travelling southeast t seconds after it leaves the origin. For 5 marks, we need to find t, and for 2 marks, we need to find the velocity of the jet ski at this time. Okay, southeast. This is quite an interesting question, hence why it's worth a few marks. What we're going to do is look at the following. I'm going to draw up now a coordinate axis. If I was travelling now on here, the line, and this is going to be now, if we look at this, this is northeast. So if we're travelling on the line that's northeast with a velocity, let's just call this v1. So I'm going to call this velocity v1. What we can see with v1 is that I'm going to have, let's say 1, 1. Let's say I'm going to have 2, 2, 3, 3, and so on. What we can see at this stage now is that the I component of the velocity will be equal to the j component. So they are the components of velocity. What we're doing is travelling now on a bearing, or the direction I should say, and that direction is down here, and that is southeast. This is the line y is equal to negative x. So we've got 1, negative 1, so 1, we'll write negative 1. We've got here 2, comma, negative 2. We've got 3, comma, negative 3. So what we can say is if travelling, southeast, we can say now that negative I will be equal to j for velocity. So that's now velocity. So let's go ahead and deal with this. Of course, you can say j or I is equal to negative j. It really doesn't matter. So what I'm going to do is the following. I'm going to use at this stage v is equal to u plus at. So if we consider what we've got here, v is going to be equal to u plus at. We're going to go ahead and find a value here of t and solve for this. If we think now, let's put this on, and I'm just going to call this now p and q. It really doesn't matter, p and q. Our initial velocity was going to be the 0, let's just check that, the 0, 5. If we put that on, yep, so 0, 5. And then we're going to have plus at. So acceleration, so plus now, we're going to have the at. So we worked out the acceleration, which was 0.1, negative 0. So 0.1, and then we're going to have negative 0.125, and that is t. So what we can say is p must be equal to now negative q, or the other way around. Negative p is equal to negative q, or p is equal to negative q if these thing is travelling on this particular line. So if we look at this, what I'm going to say at this stage is simply now, if we think p is going to be equal to 0.1t, we can say negative 0.1t must be equal to positive 5 minus 0.125t. So adding this to both sides, what's that going to give me? 1/4 t, or 0.25t, is going to be equal to 5. So dividing both sides by 1/4, t is going to be 20. So that gives me now 20 seconds. So that's one way that you could do that problem. All we're doing is travelling on this direction right here. So find the value of t, and now all we have to do is find the velocity of the jet ski at this time. We can simply plug it back into here. So if we do that, we can say now that p, let's just sub that in. So we've got that, and we just need to put in the value of t. So we've got the 0.1 and the negative 0.125, and we're going to multiply this by the time, which is 20. So what's that give us? P is going to be equal to 2. So let's do that one. P is going to be equal to 2, and then we'll do on here. So if we get 5, then we're going to minus 0.125 times by the 20, and we'll see what that gives us. What's that going to give us? That's going to give us 2.5. So that works out. Let's just put that on, and then we're going to have, so let's put that q. Let's put q. Q is going to be 2.5. So we can say that this is 2i plus 2.5 j meters per second, and that is the velocity. We're just subbing it in. You could have subbed it in just here. I've just written it out to do that. So that's quite a nice little question. So there we go. That's looking at using the constant acceleration equations, or SUVAT equations, when we've got motion in 2 dimension rather than just 1 dimension. As stated throughout the video, just collect the information using SUVAT. You can either use the I and J notation or column notation, and that will allow you to solve these problems like so.